counted by closed forms, dB equals 0. And it's actually counted by cohomology, which is counted by the number of Betti numbers, or the number of cycles that the form can sort of wrap on. So for an antisymmetric tensor B mu nu, as an example, I can decompose into one form, and 0 forms in space-time, with the corresponding 0 form, 1 form, and 2 forms in the internal manifold. The number of 0 modes are counted by 0, 1, and the second Betti number. So I might try to say a little bit more about that tomorrow. Let me just wrap up by saying the metric fluctuations are counted by the linearized Einstein equation, as it always is. And that's known as the Schneerowitz operator. And I can also count 0 modes of that as well. So we're going to put that all together. And maybe I'll say this tomorrow. So let me just stop probably with this idea over here. Is that basically like looking at scalar fluctuations, antisymmetric tensor fluctuations, and metric fluctuations on my internal space. I can count 0 modes, and I can find the 0 mode spectrum in my Calabi-Yau compactification. And then in principle, I can do the Kaluza-Klein tower as well. But in most cases, at least from a phenomenological point of view, all we really need are to understand the 0 modes, because we can usually have enough of a mass gap to integrate out the heavier Kaluza-Klein states as well. Tomorrow, I'll mostly focus on sphere reductions. And in the sphere reduction case, I'll show you that you cannot always have a nice mass gap to remove the Kaluza-Klein tower. Sometimes things get mixed up in sort of more interesting ways. So I hope I've at least given some flavor of the Kaluza-Klein approach on sort of simple circle and torus reductions, and then also a little bit of an idea of counting supersymmetries and how we would try to reduce supergravity theories while preserving some amount of supersymmetry. All right, I'll pick up again tomorrow.
The lecture was very clear, but still maybe you have questions and comments.
So you have talked about the holonomy, which is a parallel transport around the infinitesimal cycles. So how about the non-trivial cycles?
Can you repeat it?
Yeah. You have talked about holonomy, which is a parallel transport around the very small cycles. So how about non-trivial cycles and the manifold?
Sort of more global issues,
Yes.
or something like
For
that.
example, torus, there are many cycles.
Right. I'm not sure I have a good answer to that. There are some global issues where you actually make big loops in non-contractile cycles. So there's but I believe, at least in these cases, the sort of the local or the small loops gives you all the information you really need. I'm not too sure about the global picture.
So can we turn the global boundary condition with the rotation condition to realize a partial supersymmetry breaking even torus?
Even a torus, if you had something like, for example, a Schwartz type reduction, so you sort of twist a little bit as you go around one of these torus cycles, and you can break supersymmetry. Usually you don't gain any new supersymmetries, but you can break supersymmetries. So conditions of going around big cycles, sometimes, like boundary conditions of going around big cycles, can actually destroy supersymmetries that you thought were there from a local analysis. That's usually what happens.
More questions? I have one question about holonomy. So, holonomy plays important role concerning the supersymmetry after reduction. But you mentioned that holonomy is studied in mathematics maybe 30 years before the physics. Do you know, for what purpose mathematicians are interested in holonomy?
I think mathematicians are always interested in geometry. I don't know exactly what they were looking for.
But at that time, 30 years before, supersymmetry was not known, right? Even mathematics or physics. So maybe for a different point of view.
Well, it says something about the structure group of the manifold. And so I think partially it's this idea of classification. Even so simple to pose like questions of mathematics can be very sophisticated sometimes. It's like in 2 Euclidean dimensions, Riemann surfaces are basically fully characterized by their genus topologically. But in 3 dimensions or 4 dimensions, understanding the topology of these surfaces can be more complicated. And so holonomy is saying something about the geometry, something about the structure of the manifold. I think there's mathematical interest in that, regardless of supersymmetry.
If no more questions, maybe we thank this lecture again. And we meet at what time? On schedule or? So we meet at 11:15. Slightly after. So we should be back at 11:15. Thank you.